Good afternoon, dear students. How are you? I hope everybody is fine. Now we are moving towards the last unit of the paper Inorganic Chemistry 1 BSCH 203, that is P block element part 2. In the unit 4, we have started already the P block element part 1, in which we have learned the elements which come under the P block, how they go for having the classification, and then what are the general properties we have learned of the P block element possesses, as well as we have seen various diagonal relationship between the elements found in the P block. Now we move towards the part 2. So the various topics we should go for covering in this lecture in part 2, that is group 13, that is the boron family. We should go for the introduction of this family, the group 13, compounds of the boron, boron hydrides. Specifically, we go for understanding diboranes, its preparation, properties, structure, uses. Then borazine, which is also called inorganic benzene, its preparation, properties, structure and uses, and hydroboranes or borohydrides. What is the learning outcome of this lecture? The students will able to understand about group 13 boron family with their various compounds of the boron, including the hydrides, diborane, borazine, its preparation, properties, structure, uses, hydroboranes, borohydrides and its properties. So let's start the unit 5 P block elements. Second, in that we go for boron family and the boron compounds. The group 13 is a boron family in which we have the elements boron, aluminium, gallium, indium and thallium. If we are seeing its electronic configuration, it is having the outermost electron 3. Understood? So having the outermost valence electron 3, it can able to lose the 3 electron. So as we have seen, these elements having the 3 electron in the outermost shell, so it can lose easily the 3 electron. The aluminium also, gallium also, indium also and thallium also. But boron is having the higher ionization energy. Why? As you have this property that as we move down the group from top to the bottom, ionization energy goes on decreasing. So boron is having high ionization energy as compared to aluminium, gallium, indium and thallium. That's why it is not easy for the boron to lose the 3 electrons. So it has the capability to form covalent bonds like BH3. Here you are seeing it goes for sharing with the hydrogen. With 3 hydrogen it go for forming, so it forms the covalent bond BH3, BF3. So this is one important difference found in the boron family. Boron has the different nature. It is always has the capability to form covalent bond by sharing. But if we talk about aluminium, gallium, indium and thallium, because of its ionization energy is less as we are moving down the group, as its ionization energy is less, so it has the capability to form both type of bond. It can have the ability to lose the 3 electron and form the ionic bond, as well as it's go for sharing also. So it has the capability of forming both type of bonds, ionic and the covalent. So after understanding the boron family and the difference in the property of boron and the other elements in the same group 13, now we study the various compounds of the boron and their existence. So the first boron compound is a boron hydrides. What are boron hydrides? It's a hydrogen containing compound of boron, and boron formed this hydride by the reaction of the hydrogen with these two general formula. The first formula is BnH2n plus 4, where N is equal to 2, 5, 6, 8, 10, 18. And if the number of the atoms of the boron and the hydrogen means N can be the 2, 5, 6, 8, 10, 18. In this category, the compounds are specifically called boranes. So BnH2n plus 4, where N can be 2, 5, 6, 8, 10, 18. These compounds are specifically called boranes. They are very stable compounds of the boron, very stable, and have the high melting points. Because of its stability, these compound possesses the high melting point. The second category of the boron hydride having the general formula BnH2n plus 6, where N is equal to 4, 5, 6, 9 and 10. And in this category, these boron hydrides are called hydroboranes. So this is the second category of the boron hydrides that are called hydroboranes. Understood? So we have two types of the compounds of the boron hydrides having the general formula BnH2n plus 4, which are called boranes, and the second one having the general formula BnH2n plus 6, which are called hydroboranes. So the example of the boranes we have seen with the general formula BnH2n plus 4. The first example is B2H6, which is called diborane, having 2 atoms of the boron. H is having 6 atoms. If we B5H9 is called pentaborane. It is called pentaborane. B6H10, which is called hexaborane. Example of the hydroboranes with the formula BnH2n plus 6. If we go for B4H10, that is tetraborane, hydroborane. Example it is B5H11, pentaborane is an example of hydroborane. B6H12 become hexaborane. So that become with the general formula, it is having the difference between the boranes and the hydroboranes. These both are the boron hydrogen compounds, and they are electron deficient compounds. They are having, so when they are having the electron deficient, they go for acting as the Lewis acid. So let's start the first compound, boron hydride, that is diborane B2H6. It comes in the category of the lighter borane. What are lighter boranes? When the boron atom is up to 5, B5, it comes in the category of the lighter borane, and above 5, from 6 onwards, we have the higher boranes. So this is, again, you must know what are lighter boranes. So diborane is a lighter borane. So it react, lighter boranes always react with the air spontaneously, and higher boranes are stable in the air. They are unreactive. So we can say diborane easily go for reaction with the air spontaneously. So now we see the preparation method of the diborane. The first method we can prepare from the boron trichloride, that is boron halide. When we react this boron trichloride with the sodium hydride at a temperature of 197 degrees centigrade, we get this boron diborane. and NaCl. The second method of the preparation is by the reduction with the lithium aluminium hydride. The same boron trichloride, when react with the lithium aluminium hydride, we have the diborane, lithium chloride and aluminium chloride. So the major thing of both the preparation is we can prepare from the halides of the boron. Boron trichloride, it is stable halide, we can say. We can react with any kind of the hydrogen containing compound, sodium hydride, we get diborane. And using lithium aluminium hydride also we can get the diborane. So these are the important preparation method of diborane. So let's see what are the physical properties of the diborane. As it comes in the category of lighter borane, it reacts with the air spontaneously. It is a spontaneously flammable gas. So it reacts very easily. It's highly reactive. Its melting point is minus 165.6 degrees centigrade. Its boiling point is minus 92.5 degrees centigrade. So it is stable only at the low temperature in the absence of the moisture and any kind of grease. If it is having in the absence, it is only stable at the low temperature. Now we move towards the various chemical properties of the diborane. Action of the heat, we can say when it goes for having, because it is stable at the low temperature, when it goes for heating at the high temperature, diborane decompose into the other higher boranes, as B2H6 goes with the B4H10, B5H9, that is pentaborane. So decomposition causes the higher boranes. This is the first chemical property. At the high temperature, it converts into the higher boranes. It decomposes and converts into the other boranes, or that is higher boranes. So the next property is the action of the oxygen. As a diborane is highly reactive, it reacts easily in the air. When it reacts with the oxygen to form boron oxide, water, and a high amount of the heat is released. So this reaction takes place spontaneously, as it comes in the category of the lighter boranes. The third chemical property is the action of the water. When the diborane reacts with the water, it goes for forming the boric acid and the hydrogen gas is evolved. This is the third chemical property of the diborane. So let's understand the structure of the diborane. It has having the two boron atoms and the four terminal hydrogen atoms which lie in the same plane. You are able to see here the two boron atom are here, which is having the bond with this hydrogen, two hydrogen right hand side, and the two hydrogen we are having the left hand side. So it is in the same plane. But when we see the center edge atoms, that is bridging hydrogen atoms, they are not in the plane. Understood? So here we can see here the bridging hydrogen atoms, one, and the another hydrogen atom is here, which is forming the bond with this boron, and they are connecting to have this bridge. And each one of the hydrogen atoms go for combining with the two boron atom, and in this we can say the three center is there. Three center means this hydrogen is bonded to this boron, another to this boron, the center become 3. Understood? So 3 center where the electron is only sharing the 2. 2 electron is only sharing. Center is 3 but 2 electron is sharing in the bridge. That's why, and this is not in the plane. That's why this is called banana bond, where the 3 center is there, 2 electron is there. Such kind of bond is called banana bond, and it is not in the plane. It goes on fluctuating. So this kind of bond is present in the diborane, and the structure is like this. Now we see the various uses of the diborane. It is used for the preparation of the high energy fuel and the propellants, and it goes for giving out the large amount of heat. It is used for the preparation of high energy fuel and propellants. It is used as a reducing agent in various organic reactions. So it acts as a reducing agent also. It acts as a rocket fuel for the various supersonic bombers because it react spontaneously. That's why it is used as a rocket fuel for the supersonic bombers. It is used as a catalyst in the various polymerization reactions to form the polymers. It acts as a catalyst there also for the preparation of the higher boranes, as we have seen in the chemical property. When we heat at the high temperature, the borane can be decomposed into the various higher boranes. Now we see the second compound of the boron, that is called borazine, or it is also called borazole. Its formula is B3N3H6. It was earlier named borazole because it is actually its properties resemble to those of the benzene. This is very important thing. It is also called inorganic benzene. Understood? So the earlier name of borazine is borazole, and why it is named as a borazole? Because its property resemble with the benzene. It is also called inorganic benzene, B3N3 and H6. So let's see what's the method of the preparation of borazine. The first important method of the preparation is given by Stock and Paul, which is called Stock and Paul method, in which it is prepared by the diborane. When the diborane reacts with the ammonia and goes for heating, we have the intermediate, and it is go for heating at 200 degrees centigrade. We form the borazine, and hydrogen is produced. So it is the method called Stock and Paul, which is prepared by the diborane when react with the ammonia and go for heating. We have the borazine. The second method is from lithium borohydride. When the ammonium chloride and the lithium borohydride is heated up to the temperature 230 degrees centigrade, we have the borazine lithium chloride. Again, hydrogen is released. So this is the second method of the preparation. So these two methods of the preparation are there for the borazine. Now we see its physical properties. It is the colorless liquid with the boiling point. We have the boiling point 64.5 degrees centigrade, and the melting point is 58 degree centigrade. So it's a colorless liquid with this boiling and melting point. If we see its chemical property, the first chemical property is the decomposition. It decomposes very slowly at the room temperature. It is stable enough, so at the room temperature it decomposes very slowly, and when it decomposes it gives the diborane and the hydrogen as well as other volatile products we can get when it decomposes. Now the next property is action of water. If we react the water to the borazine, it forms boric acid, and the ammonia is released, and the hydrogen is also released. So it reacts with the water to form boric acid, ammonia, and the hydrogen. And if we see its structure of the borazine, here you are able to see the structure of the borazine. Here you have it is similar like benzene. We have this double bond with the nitrogen, then single bond, alternative single and double bond we are having in this structure, and all are having with the hydrogen with this bond length 1.44 Armstrong is the bond length found with the double bond, and the single bond we are having 1.02 Armstrong, which resemble with the benzene. As you are able to see the benzene alternative here, the bonding is occurring like this. So it is very isoelectronic with the benzene. The structure is isoelectronic. That's why it is called also inorganic benzene. It has a planar structure like benzene, and it has been proved by the experiment X-ray crystallographic method. Understood? So that's why it is called the inorganic benzene. Now the next category of the compound is borohydride. They are also called hydroborates. When the boron hydride ion react with the alkali or alkaline earth metals, it forms these compounds called borohydrides. So let's see the one kind of the borohydride, that is alkali metal borohydride, because when the ion is go for reaction with the alkali metals or alkaline earth metals, we have two type of borohydride, alkali metal borohydride and alkaline earth metal borohydride. So let's see here how it is prepared. From the lithium hydride, when react with the reaction with the diborane in the presence of the ether, it forms the lithium borohydride. Understood? So the lithium is an alkali metal. When the interaction of the alkali metal hydrides or the hydroxides on diborane in the suitable solvent like ether, it forms lithium borohydride. Likewise, you have the hydroxide example. Here I have taken the sodium hydroxide react with the diborane to form sodium borohydride. Understood? So either from the hydroxide or hydride of the alkali metal, when reacts with the diborane in the suitable solvent, we have alkali metal borohydride. Now, what are the properties of this alkali metal borohydride? They all are the white crystalline solids having the ionic nature. Lithium borohydride or sodium borohydride, they all are having the ionic nature, means ionic bond is formed, soluble in water and the other organic solvents. These hydrides converts the metal to their oxidation state, free halogens to their corresponding halides, as well as it goes for forming more. They have the great importance for their reducing action in number of the analytical and the synthetic purpose. So act as a reducing agent, because we have seen lithium borohydride, it is a famous reducing agent. It goes with the reactions in number of the synthetic process. So they are the white crystalline solids, ionic in nature, ionic bond is there, soluble in water and the other organic solvents. It can easily convert the metal to the oxidation state or either free halogens and more halides and act as a reducing agent. So the next category is the alkaline metal borohydrides. In here we have taken the example of beryllium. We have taken beryllium, beryllium borohydride is obtained when the chloride of this metal react with the sodium boron hydride at a high temperature. Beryllium, it is formed as well. It is covalent in nature, inflammable and volatile. And the magnesium borohydride is also formed when the alkyl magnesium goes with the reaction with the diborane. We have the magnesium borohydride. So this come in the category of alkaline. We have the beryllium borohydride that can also be prepared which is covalent in nature and inflammable, and magnesium borohydride is also prepared. So we have the properties of the alkaline earth metal borohydrides. It's a white crystalline solid having the melting point 180 degrees centigrade. Above this temperature, it goes for the decomposition. It's slightly soluble in the solvent like ether, calcium, strontium, and the barium borohydride exhibit very similar properties, but in nature these are thermally stable. So this is all about the boron compounds, and the group 13 we have talked in the p block elements. In the next lecture we have the group 14 carbon family. We and the carbon compounds. We have to talk about the various compounds, its properties, and various uses. Thank you and take care.